Okay, and we're back. I just wanted to give you a chance to look at the bottom of that page because I realized I was cutting off some words last time. So there you go. In less dense media, light bends away from normal, it speeds up, and there's a larger wavelength. Like I said last time, now we're going to go and do some some interesting problems that have some interesting consequences here. So, number one, a specially designed flashlight shines from underwater and points towards the water's surface. Determine what will happen if the angle of incidence is 48.75 degrees, as well as what will happen if the angle of incidence is greater than this, and make a rough sketch of both situations. So let's actually do the sketching part first. So here will be our boundary. You get the point. Okay, here will be our normal line. And we have a flashlight that's in the water. Let's say that this is water. This is air up here. Remember, water is 1.33 for its index of refraction. Air is 1.00. The angle of incidence is 48.75 degrees. And those flashlights shining from inside the water. So that means that we have, let's see here. Okay. So that means that 48.75, that's about there or so. Here's our incident ray. Okay. So, here's what we want to know. What will the angle of refraction be? We can use Snell's law to find that. N1 sine theta 1 equals N2, right or wrong, N2 sine theta 2. Now, because the incident ray is in water, that means N1 is going to be 1.33 multiplied by the sine of 48.75 degrees equals N2. Well, wait a sec. N2, the refracted ray is supposed to just be in light, so that's just 1, and then times sine of theta 2. So essentially, since the 1 can just kind of be dropped off, we just need to multiply 1.33 times sine of 48.75 degrees, and then take the inverse sine of that, remember, because we got to get rid of this sine, and figure out what theta 2 is. Seems pretty simple. So let's start with the sine of 48.75 degrees, multiply that by 1.33, and we end up with 0.99999, some very, very close to 1, interestingly enough. And we need to take the inverse sine of that. And it comes out to be 89.409. And I think you could probably see where I'm going with this. Obviously, I just couldn't write out, I didn't want to write out, a million decimals to make this, I wanted to limit it so it's a manageable number to type out and for you to type into your calculators. But the angle of incidence is rapidly approaching 90 degrees here. And as a matter of fact, that's what I'm going for here. I'm going for 90 degrees being approximately what theta 2 is. So this would be an interesting case, right? If your angle of refraction is 90 degrees from the normal line, that means it just kind of skims the surface. Well, that's kind of weird. So what's happening here? Light never really makes it out of the water. Instead, it just kind of skims along the boundary. This has a name, okay? The incident angle, the angle of incidence in this case, is referred to as the critical angle. If this happens, not in every case, but if this happens, then the angle of incidence is referred to as the critical angle. So that's kind of interesting. By the way, this only happens when light goes from high N to low N. Okay. So we get the critical angle. Okay, that's cool. But what happens if the light is, if the angle of incidence is bigger than that? Because very clearly, and you can do the math, if the angle of incidence is smaller than that, the light will fully make it out. But what if you take this angle of incidence and you increase it even more? If theta I is greater than about 48.75 degrees, well, let's see what happens. Let's pretend that this was, let's say, 49 degrees. So I do sine times 49 times 1.33. And I get 1.0038 approximately. If I try and do second sine of that, I get an error. And it makes sense why you get an error because, well, let's do that again. If I'm trying to take the inverse sine, that means I'm looking for the angle. If I were, so that essentially what that means is I'm looking for an angle that if I were to take the sine of that angle, I would get this number. Something you've got to remember about sine is that it never gets higher than 1, never gets lower than -1. And in that case, if this is higher than 1, then there is no angle that would make sine equal to this. It just wouldn't work. It doesn't exist. Essentially what we have here is something that can't happen. What this is trying to show you here is that if this were the case, if you had an incident angle that was bigger than about 48.75 degrees, then what's going to happen is that there is no refracted angle. So even if you had something bigger, then it will be impossible to solve for theta 2, which means no refraction. Well, if there's no refraction, the light's got to go somewhere. What ends up happening is that all the light reflects off the boundary. It doesn't refract, it reflects. So let's say, I'm just going to sketch this in. Let's say you had theta I of 50 degrees, okay? Then what would happen is all that light, none of it would get out into the air. You would simply have the light be reflected back down. Okay? This phenomenon, so if you have light that just skims the surface, the incident angle is called the critical angle. Okay, and you can measure that for any set of materials or media where you have light going from a high N value to a lower N value. If you have this instead, where none of the light makes it out, it doesn't even skim the surface, just gets reflected back down, that, on the other hand, is called total internal reflection. And it's actually the reason why diamonds sparkle. Diamonds, if you remember, have a very, very high N value. I think it's 2.42 or something about that. The higher the N value, the higher the index of refraction, the easier it is to achieve total internal reflection. So the reason the diamonds sparkle so much inside is because once light gets into a diamond, it essentially gets trapped there. It reflects around all these surfaces before finally coming out. So because light reflects around all these different surfaces, you have light coming at you from many, many different points on that diamond, which is why they're so sparkly. Okay? You can also see total internal reflection if you go in the summer down to the bottom of a pool and look up. You'll notice that you'll be able to see the sky right above you, but to the side of you a certain distance, you actually won't be able to see the sky anymore, even if it's not where the pool edge is. What you'll see instead is just the walls or the floor of the pool being reflected back down to you. That's because the light physically cannot get to your eyes in terms of how it's being bent from those locations. Very interesting. Okay, so let's do one more example here. It says light passes from air through a slab of zircon, then back out into the air. A diagram showing this, including the incident ray, is shown below. Trace the path of the light ray through the slab. So first thing I'm going to do is I'm going to extend this light ray out to about there, just so it's easier to read. Let's get so we have air. Air has an index of refraction of 1.0. Zircon, I don't know zircon off the top of my head, but if I look on my reference tables, I see it's 1.92. So, we've got the indices of refraction. Let's measure the angle of incidence. Okay. Looks to me like it's about 36, 37. You could even call it 36 and a half if you really want to. So I'm going to go with theta I equals 36.5 degrees. Okay. Now, I use Snell's law. N1 sine theta 1 equals N2 sine theta 2. N1, the incident ray is in air, so that's 1 times the sine of 36.5 degrees. N2, the refracted ray, that's in zircon, so it's 1.92 times the sine of theta 2. So you can write out the math if you want to. I'm just going to do 1, okay, so that's just 1 times sine of 36.5 divided by 1.92, and we take the inverse sine, and we get 18.05, so approximately 18 degrees is theta 2. Now we draw that. Let's see, 18 is about right there. So I'm going to draw this, and make sure you're careful about how you draw this. Draw it from right where the incident ray enters to, you don't draw all the way to that dot, you only draw inside the zircon, because what's going to happen when the light gets back out, it's going to refract again because it's changing material. So theta for the refraction here is about 18 degrees. When we get to the zircon air boundary, we're going to need another normal line. And if you remember anything from geometry, this angle here and this angle here are the same thing. But notice this is the angle for refraction here, the angle that the light bent at. Now when it's coming to this boundary, we now have it as the angle of incidence. Those are alternate interior angles. And so I can run the calculation again. N1 sine theta 1 equals N2 sine theta 2. N1 this time is 1.92 because we're starting in the zircon, times the sine of what I rounded to, 18.05 degrees, equals N2, that would just be 1, times sine theta 2. So now we do 1.92 times the sine of 18.05, and then we take the inverse sine of that. And interestingly, maybe not interestingly, seeing as we used pretty much all the same numbers, just in slightly different, not even in slightly different spots, in pretty much the same spot, we come up with 36.5 degrees equals theta 2. So this refracts again. And notice it curves away from the normal line, opposite of what happened last time. So we have theta refract now is back to our 36.5 degrees, which is interesting because that means that the first incident ray and the last refracted ray are actually parallel, and you can see that if you look at those lines. They are parallel, but that line has been shifted. If this were our lab, this is one of the things that you actually see during this lab. Okay, so that's something that's a little bit interesting. I want to close just with one little, one kind of general concept that you can follow. Typically, if you want something to refract, to bend more, if you have a bigger incident angle, you're typically going to have more refraction. You can do the math and prove that yourself. But bigger incident angle means there's going to be more refraction. And if you have a larger n difference, a larger difference in index of refraction, it's not just how big n is, it has to be a big difference between the two n's. A larger n difference also means more refraction. The equation here is not the hard part, and the drawing here isn't the hard part as long as you know what you're doing. Unfortunately, like I said, in your guys' circumstance, you're not going to be doing too much drawing, but the math itself is not hard. Remember the concepts. If we're going from smaller n to bigger n, smaller index of refraction to bigger index of refraction, then the light is going to bend towards the normal line. The light is going to slow down, and the wavelength of the light is going to decrease. The opposite happens when you're going from a high index of refraction to a lower index of refraction. In that case, the light bends away from the normal, the light speeds up, and lambda, the wavelength, gets bigger. Okay? You'll have chances to practice that. Oh, geez, I'm not even showing you the right stuff. There we go. So you can pause and you can look at that. That's pretty much it for refraction. If you have any questions, don't hesitate to ask. I'll see you guys later. Bye.